optimizers and how it works and how to implement it with KRS. So before going into optimizers, I first want to explain how training occurs in deep multilayer perceptron or neural network. So first of all, from the dataset in first step, we have to draw a bunch of say number of k examples from xi and yi's, and I have already discussed that xi's are the inputs and yi's are the labels. So first we have to take k examples from the whole dataset D. Then you have to randomly initialize the parameters which are weights and biases, and then you have to uh, run several epochs. So you have to repeat this step, which is repeat until convergence, and convergence when up to when w new equal to w old. So I will discuss how it works, and within that there are five steps. So first it will calculate the prediction, which is yp. Then it will calculate the loss. So loss formula is which Suraj already discussed, which can be mean square error. So it is nothing but yp minus yi uh, to the power whole square. And then you have to take the gradient, or you have to differentiate it with respect to the weights, and then you have to back propagate it, this loss, to change the weights until the weights are convergence. So I will discuss it with examples. Then update the w simultaneously, and this process will continue until w new equal to w old. So let's start with this example. So first of all, let's say there are input layers, output layers, and there are one hidden layers. So first input will be fed, and then in first step it will calculate the prediction. Let's suppose I want to calculate the height of patients. So it will calculate the prediction, like, which is denoted by yp here, which I have discussed yp, and actual heights are yi. So then it will calculate the loss yp minus yi to the power whole square, to the power 2. Then it will create the gradient, and then it will back propagate the gradient towards backward in this step, backward propagation step, so that these weights will update to minimize the loss, and it will continue until w new equal to w old. So now I want to explain how this uh, w new and w old works. So actually, training a neural network is nothing but learning the weights such that this loss function, which is yp minus yi to the power square, is minimized. So you actually, the main reason or main goal of the machine learning model to minimize the loss. For example, suppose I want to predict the height. So my objective would be, if the actual height is 165 centimeter, then I want to I want my model to predict the height 165, so that the loss is zero. And neural network training means nothing but to learn these weights such that the error is zero, and that is the process of optimization. So and the weight updation will take place in this formula. So this is w new, and this is w old, minus the learning rate, and into d error divided by dwx. So error, I have talked, this error means yp minus yi whole square, which is mean square error. And you are taking the differentiation with respect to the weights, with respect to these weights. And now how to calculate this differentiation. So take the simple example. Suppose there are input x, output y, and there are two layers, which is input layer f, and output layer g. And you want to, first we have to calculate the loss, and then you have to differentiate it, and then back propagate it through this network. So if I write that dg divided by dx. So if I say in word, so it will sound like the loss in this output due to the input x equal to dg by df into df by dx. So dg by df means change in output due to these weights into change in this weights due to this. So dg by df means that part, and df by dx means for that weights. So if the number of layers increases, then this multiplication will increase. So, and I think it is clear. So first, and here this you can think this dg as d error and dx as wx. So and then it will calculate the loss in this way. So it will first calculate that the change in error here due to weights here, and then change in output here due to weights here. That is how this gradient is calculated. After that this actually these steps is within this part. So and this weight equation will be updated through each epoch. As Suraj said that you have to take several epochs to see that in which epoch the optimization or the error is minimum. So this actually nothing but mathematically equation is um, this equation is running in each epoch, and it will convergence means when w new equal to w old, this training will be stopped. So for that, so now I want to see for which weights the error is minimum. Now my objective is to calculate for which w's the error is minimum. For that, these optimizers come into picture. To and the objective of the optimizers are to find the best w's, to find the best these w's for which loss or error is minimum. So here the objective of the optimizers are find these w's to minimize the error. And you can think like these w's are like a knob, and you need to adjust in such a way that the error is minimum or error is zero. And that is the whole training, that is the purpose of the training. So and to minimize this loss function, there are several algorithms like gradient descent, stochastic gradient descent, mini-batch stochastic gradient descent, ADA delta, ADA grad, RMSprop, and ADAM. And I want to say that gradient descent, stochastic gradient descent, mini-batch stochastic gradient descent, and these types of algorithms are different in a single line. So if you see this algorithm, and I have said that in first step draw a bunch of k examples from this training set. And if you say that and if you take whole training set, if k equal to n means whole data point, then it will sound like it is gradient descent. And if you take randomly one single point, then it is called stochastic gradient descent. And stochastic means you just taking randomly or probabilistically a single point from the whole training set. That is why it is called stochastic gradient descent. And mini batch stochastic gradient descent means you just taking randomly a bunch of points from the data points. That is why it is called mini batch stochastic gradient descent. And this is the difference between gradient descent, stochastic gradient descent, and mini batch stochastic gradient descent. And now the question is, for which w's the error is minimum. That is the question. So here the question now, the where are the points in which the loss is minimum. So actually, as Suraj said that and one more thing, the cost function or the optimizer function there are two types. One is called convex loss function and another is non-convex loss function. And Suraj, and which Suraj discussed in previous talk, that and that was the convex loss function. And difference between the convex and non-convex loss function is, in convex loss function there is only one global minima and only one global maxima, and it is the convex function. And these kind of functions are non-convex function. And in deep learning or artificial neural network, maximum of the most of the loss function belong to non-convex loss function, in which there are several local minima and there can be several local maxima. So you can see from this picture, you can think this y-axis as the error and the x-axis as the weights. And suppose this is a loss function, which is here d error function is called fx, and x is the this wx. So if you plot it, you will see that, and most of the time this is a non-convex function. That is why you can see that there are local maxima, several local maxima, and there are several local minima. And one more thing is there, which is called saddle point. So as I all know that in local maxima or local minima, the slope is 0, or d error by dwx equal to 0. So if d error by dwx equal to 0, then this whole term will become 0, and d new and w new equal to will be w old. So this is the convergent point, and this epoch will be, and this w will be the base w for which error is minimum, and which is our goal for the optimizers. So but for non-convex function there is a problem, and it is the saddle point. So in saddle point also, the d error by dx is 0. So what happens in most of the time, suppose you start from here, and if you uh, get here in saddle point, then you might think that this is the local minima, but local minima or global minima can be here. So in stochastic gradient descent or mini batch gradient descent or gradient descent, the problem is the training can be stopped in the saddle point, and it will not reach the local minima. That is the point in, and that is the problem in the several optimizers like stochastic gradient descent, mini batch gradient descent, and gradient descent. And now, and for that reason there are several new optimizers came into picture, like I have said, ada delta, ada grad, RMSprop, and adam. And now the most heavily used or most widely used optimizer is called adam, and I will discuss those in upcoming examples. And so this is the thing. So and one more difference between convex and non-convex function, you can say that. So in convex function, if you take any 2 points within this region, and if you try to connect with a line, you will see that the whole line will lie in this region. But in case of non-convex function, suppose if you take a point here and a point here, and if you try to join this line, some portion of the line will be outside this region. So that is why it is called non-convex. And this is the most simple example if you want to uh, say that how the non-convex and convex function are different. So as I said, and in deep learning most of the optimizers function is non-convex. So that is the problem with saddle points, and I will also show it at last that how stochastic gradient descent and mini batch gradient descent could get stuck in this saddle point, and it will not reach the local minima. So as I said that d error by dw is 0 in minima, in maxima, and also in saddle point. And in saddle point is neither maxima and minima. So in saddle point there are several algorithms which could get stuck. So now some optimizers and how to calculate d error by dw. So first I have taken this data set d equal to xi yi and then n data points, and now you want to calculate d error by dw into some learning rate. And one more thing, that for stochastic gradient descent, and as I said, that first we have to take k points from the training data set. If k equal to n, then it is called gradient descent. And if you take the average of gradients of all n points and take the mean and update the w, then it is called batch gradient descent. And then, and if you take randomly or probabilistically one point from the whole data set and calculate the gradient, then it will called stochastic gradient descent. And if you take a subset of points from the training point and you do the training, then it will be called mini batch stochastic gradient descent. And one more disadvantage is with that is mini batch stochastic gradient descent or stochastic gradient descent could get stuck at saddle point. And if you see it is a contour plot, and which is on what is contour plot. So you can see it is a 3D plot, and in this axis, in this plane, you can see that there are circles, several circles. So if you transform this 3D into 2D, then this contour plot will create. So in contour plot, the middle portion, this is called minima, and this circle says that in this point w's are or weights are same. So your training will start from this outside this circle, and it will try to reach minima, and it will take several epochs, and each arrow you can think of as one epoch. So you can see that this blue line denote the batch gradient descent, green is mini batch, and this I think purple is stochastic gradient descent. So so you can think that you can see that for stochastic gradient descent, as it is taking one random point from the training data set, and it will do the whole process. It will take several steps, 1 2 3 4 5 6 7 8, like that, for to reach the minima. But in case of batch gradient descent, you can see that 1 2 3 4 5 6 7 8 9 10, within 9 steps it is going to the minima. And for mini batch also, it is lower than stochastic gradient descent. So it is it is very clear that stochastic gradient descent is taking too much steps to reach the minima. And one more concept is there, which is called momentum. So in stochastic gradient descent, if you give some momentum is nothing but a weight to the points, so that it will reach the minima very quickly. That is called momentum. And this momentum concept is used in stochastic gradient descent and this upcoming optimizers also. And one
Sir,
more. Yes. Yes, hello.
hello.
Yes, yes, yes.
Sir, epoch means number of updates, right?
Yes, yes, number of
Like
updates. So
one
for
step,
so
like
for
from one W to another W.
yes, yes, for you can think this 1 2 3 4 5, these 5 steps will be done for one epoch. And it will, and this equation will be updated, and again the whole 5 steps will be done, and then again this equation will be updated, and for each epoch the w's will be updated accordingly.
Okay.
So so uh, so uh, due to having some problem with this gradient descent and stochastic gradient descent, some new optimizers are invented. For example, adagrad and adam. And one more thing, in adagrad, so I have said that there is formula in this formula, there is a eta or a, which is called learning rate, which Suraj already have discussed. And in this type of optimizers like adagrad and adam, this learning rate can be adaptive. for means in each epoch it will automatically take a different learning rate depending upon the minima point or global minima point. It will automatically change the learning rate. But in case of stochastic gradient descent or mini batch gradient descent, it will not do that automatically. And and now the point is, an adam is the most widely used optimizer nowadays, and for that there are several reasons. One is adaptive learning rate and momentum is used, and then it is very straightforward to implement, and it is computationally efficient and little memory requirement is needed. So and there is a plot which is actually from the original paper of adam. So you can see from this picture there are several optimizers, adagrad, RMSprop, ada delta, adam. And in y-axis there is a training cost, and in x-axis the iterations over entire dataset. So you can see that within 50 epochs the training error is significantly low than other optimizers. So that is why, and I will also show in my coding example that how first the adam optimizer reach the minima. So and also you can see from this picture that within 50 epochs the training error or loss is significantly less than other optimizers, and which is for mnis dataset, for cnn, which I have already discussed in previous lab. So this is for mnis dataset, and this is the actual link of this paper. You can see it. So now I want to implement these several optimizers using Keras. So as I have already told, Keras is a API, and it uses TensorFlow backend. And so to use Keras, you have to import these modules, sequential, conv 2D like that, and then you just take the mnis dataset and then split it into train test, and then shape your array to 28 by 28 to 28, and this is for training purpose. And then and this steps is done due to plot the tensor board, so to visualize the how epochs are running with respect to accuracy. And I have taken this one, two, three, four, five optimizers I have taken, and the model is a CNN model. So first one is a sequential model, and then we have used a conv 2D model with 16 kernels of size 3 into 3. Activation is ReLU, and then max pool layer like that. And at last there are 10, 10 and softmax, because in mnist, as I have said, that there are 9 digits, 0 to 9, and we have to predict which number from which the picture belongs to. And then we have used several these 5 optimizers to see which one um, was the best. And for that we have just run 5 epochs of batch size 32 and plotted it. So you can see that the third one is adam and last one is sgd. And I want to uh, show the difference between the two. So third one is adam, so 1, 2, 3. So you can see that within 5 epochs only the accuracy is nearly about 98.07%. And loss started, and in first epoch the loss is 0.9679. So and one more thing. So for each uh, and this one epoch is for, this is for one epoch, and after that from 1 to 2 it is taking 21 second, 34 for microsecond. And within this time this whole 5 steps, will take place. First it will calculate the yp, then calculate loss, then calculate the gradient, then it will back propagate it, and then it will simultaneously weight the change the w's. And these 5 steps will be done for each and every epoch. So you can see that and for sgd you can see that for 5 epochs it is only 89.36% accuracy. and loss started from 4 here, and for Adam the loss is 0.96. For first epoch only the loss is very minimum, and the accuracy is 88.45%, which is nearly 89.36 after 5 epochs in SGD. But in first epoch Adam is reaching this type of accuracy, and within 5 epochs you can see that that accuracy is 98.07% for Adam. And this is the, and similarly for other optimizers you can see also that the accuracy, and for the Adam I think this is the maximum. And one mode optimizer is there, their RMSprop, which is uh, have same accuracy you can say from the for that example, slightly higher. But in general, if you have very large number of data set and training parameters are higher, then I think Adam is the best option, because there are several advantages I have said, because it is computationally very efficient, and then it takes very less memory requirements, and like that. And I have also plotted this tensor board to show the you can plot it to see your structure. Like I have used this con 2D, then max pooling layer, then con 2D, like that. And this plot is for accuracy for several epochs. And one more thing I want to show that. So here from this picture you can see that, and this is a 3D plane, and this is a non-convex.
Sir,
Yes.
okay. Now it is visible.
Okay. So you can see that that point is called saddle point, and then local minima is in this direction. So you can see that the SGD is in red, and SGD is stuck in the saddle point, and it will not come outside the saddle point to reach the minima. But for several other optimizers like Ada Delta, Ada Grad, uh, these are coming very fast toward the minima. But the problem with SGD for non-convex function is that it can get stuck in the saddle point, and it will not reach the mm, global minima. And it is another visualization. You can see that, and this is the minima, and there are several optimizers, and how fast each optimizers are reaching to this minima. You can see that from this picture. So I have also given the link of this website in my notebook. You can see that. So now I think that that's it from my side. So you have any, if you have any question you can ask.